All right, let's dive into one of the most powerful ideas in all of probability. Seriously, it's this concept that shows up absolutely everywhere, from a doctor's diagnosis to checking products on an assembly line. It's the idea that a single tiny piece of new information can completely flip the odds on their head. We are talking, of course, about conditional probability.
Just look at these two questions. On the left, you've got a classic, right? What's the probability of picking a king from a deck? Easy. 4 kings, 52 cards, done. But then look at the right. We just add 5 little words, given it's a face card. And bam, it's a whole new ballgame. That one condition changes literally everything. So, how?
Well, the secret here isn't some crazy, complex new math. It's actually way more intuitive than that. That given information, it acts like a filter. It tells you to just ignore a huge chunk of possibilities that aren't relevant anymore. Your entire universe of outcomes shrinks down to this smaller, more focused world.
Let's just walk through it. Okay, we start with all 52 cards. Then we apply our filter. We are given that the card is a face card. Poof, all the 2s, the 7s, the aces, they're gone. We don't care about them. Our world shrinks from 52 cards down to just the 12 face cards. You know, the jacks, queens, and kings. Now, in this new, smaller world, how many are kings? Well, still 4. So the probability isn't 4 out of 52 anymore, it's 4 out of 12. See? The world changed.
And that, right there, is the heart of conditional probability. It's just the probability that some event F happens on the condition or given that another event E has already taken place. We literally just did this. Event E was we drew a face card, and event F was that card is a king.
Now, this shrinking universe idea is an awesome way to think about it. But, we also need a formal tool to get the job done when things get a bit more complex. And here it is. We read P, that vertical line E, as the probability of F given E. And all it is the probability of E and F happening together divided by the probability of E happening at all. This little formula is the engine that drives everything we're about to do.
So let's put that formula to the test with some real data. This table lays out a survey of 800 people, broken down by gender and whether or not they smoke. We're going to answer this question. What is the probability that a randomly chosen person is a smoker, given that we know they are male? So, our formula tells us we need 2 pieces of information: the probability of being male and a smoker, and the probability of just being male.
Okay, let's plug in the numbers. The chance of being a male smoker, that's 120 people out of the total 800. The chance of being male, that's 400 out of the 800. So, we divide the first by the second. The out of 800 parts cancel each other out, which is pretty neat, leaving us with 120 divided by 400. And that gives us our answer, 0.3, or 30%.
Okay, so we've got a handle on finding probabilities after a condition is met. But what if you want to find the probability of a whole story playing out? Of 2 events happening one after the other, especially when that first event changes the odds for the second one. For that, we use something called the general multiplication rule. And hey, if this formula looks a little familiar, it should. It's just our conditional probability formula, but rearranged. We just did a little algebra. This rule tells us that the probability of a sequence, first E happens and then F happens, is just the probability of the first event multiplied by the probability of the second event happening in that new, smaller world that the first event created.
Thinking of it as a story is a great way to wrap your head around it, but these sequences can get messy pretty fast. We need a way to map out all the possible paths the story can take. So, how can we actually visualize this?
The answer is a tree diagram. They are the perfect tool for the job. Every fork in the road is a new branch, representing a possible outcome. And here's the absolute key, the most important thing to remember. After that first set of branches, all the probabilities on the next levels are conditional. They totally depend on the path you took to get there. And to find the probability of one complete story, one full path, you just multiply the probabilities along its branches.
Let's see this in action with an example. Imagine a quality control check. We're going to pull 2 circuits from a batch of 100. In that batch, we know 5 are defective and 95 are good. Now, the key phrase here is that we are sampling without replacement. Once we pick a circuit, it's out. It doesn't go back in. And that means the odds for the second pick absolutely depend on what happened with the first.
So, our tree diagram starts with that first pick. What could happen? Well, we could pick a good circuit. There's a 95 out of 100 chance of that. Or we could pick one of the defective ones, which has a 5 out of 100 chance. Those are our first 2 main branches.
And this is where it gets really cool. This is the conditional part. Look at the probabilities for the second pick. If our first pick was a good one, there are now only 99 circuits left in the batch, and only 94 of them are good,
So the probability of grabbing another good one is 94 over 99. But what if our first pick was defective? Well, there are still 95 good ones left, but only 4 defectives in those remaining 99 circuits. The probability completely changes based on the path you're on.
So, let's follow one of those stories to the end. What is the probability of picking 2 defective circuits in a row? We just multiply along that path. The probability of the first being defective is 5 out of 100. Then, the probability of the second one also being defective, given the first was, is now 4 out of 99. You multiply those two together, and you get this tiny number, about 0.002. That's a 0.2% chance. Not very likely.
So all of this has been about dependent events, right? One thing affecting the next. But we all know some things, like flipping a coin twice, are independent. The first flip has absolutely no impact on the second. So how do we prove that mathematically? How can we be sure that we don't need all these special conditional rules?
Well, there's a formal test for it, and it's beautifully simple. 2 events, E and F, are independent if the probability of F happening, given that we know E already happened, is exactly the same as the probability of F just happening on its own. In other words, finding out that E happened gave us 0 new information. It didn't change the odds of F one bit.
Let that idea sink in for a second. This quote from the source material just says it perfectly. If knowing that E occurred doesn't change the probability of F, then E has no influence on F, none. They are completely separate worlds.
And that kind of leaves us with a final question for you to think about. We now have the tools to tell the difference between events that are linked and events that are not. So as you go through your week, just look around. Is the chance of traffic on your commute tomorrow independent of the traffic today? Is your grade on a test conditional on how much you studied? How much of the world is really just a series of random coin flips? And how much is a story, where every single chapter depends on the one that came before?